4.1 Definition of capacitance. 4.11 Capacitors, the basics. A capacitor store an electric charge is a little bit like a battery, except it stores energy in a different way. It can store as much energy as a battery, although it can charge and release its energy much faster. This is very useful, and that's why you will find capacitor used in almost every circuit board. In electric circuits, the capacitor acts as the water tank and store energy. It can release this energy to most our interruption to the supply. If we turn a simple circuit on and off very fast without a capacitor, then the light will flash. But if we connect a capacitor into the circuit, then the light will remain on during the interruption, at least for a short duration, because the capacitor is now discharging and powering circuit. Inside a basic capacitor, we have two conductive metal plates which are typically made from aluminium. This will be separated by dielectric. Insulating materials such as ceramic. Dielectric means the material will polarize when in contact with an electric. Next, 4.1.2 Capacitance. Capacitance is the ability of an object to store electric charge and the ratio of the magnitude of charge on either conductor to the magnitude of the potential difference between the conductors. C equals to Q over delta V. Symbol C, metric unit in farad, abbreviation F. Farads are number of columns that can be stored per volt. 4.1.3 Capacitance for parallel plate capacitor. A capacitor is a two-terminal electrical device that is used to store energy in form of electric charge. When two metallic parallel plates of area A separated by distance d connected with a battery, the plates are charged and electric field is established between them. Such setup is called parallel plate capacitor. In parallel plate capacitor, electric field lines are pointed outward from the positive charge and emerge into the negative charge, and hence the electric field lines will be from positive plate toward the negative plate. The medium present between the two plates of a parallel plate capacitor is known as dielectric.
The next topic is calculation of capacitance. The goal of this topic is about how to calculate the capacitance of capacity having special geometry. The topic is divided by three subtopics, which are capacitance of parallel plate capacitor, capacitance of a cylindrical capacitor, and capacitance of a spherical capacitor. Let's start with 4.1. Capacitance is a property of capacitor used in electronic circuit, and understanding it is essential for circuit design. Let's begin by discussing surface charge density. Surface charge density is defined as the relation of the charge of each plate to the area of each plate. We can express it as sigma equal to Q per A, where the sigma represents the surface charge density, Q is the charge on each plate, and A is the area of each plate. Now let's move on to the capacitance formula. Capacitance of a parallel plate capacitor is given by the ratio of the charge on each plate to the potential difference between the plates. We express it as C equal to Q per delta V, where C represents the capacitance, Q is the charge on each plate, and delta V is the potential difference between the plates. To understand how the capacitance formula is derived, let's start with the equation C equal to Q per delta V and rearrange it. We know that the electric field between the plates of a parallel plate capacitor is given by E equal to Q over D times E naught times A, where D represents the distance between the plates and E naught is the permittivity of free space. By substituting the expression for E in the capacitance formula, we get C equal to E naught times over D times A over D. Now, let's interpret the capacitance formula and understand its implication. Capacitance is directly proportional to the area of the plates. This means that a larger plate area leads to a larger capacitance, allowing for increased charge storage. On the other hand, capacitance is inversely proportional to the distance between the plates. A smaller plate distance results in a larger capacitance, enabling higher charge storage. Capacitance is a fundamental property of parallel plate capacitors, independent on surface charge density, plate area, and plate distance. Let's move on to the next topic, which is capacitance of cylindrical capacitor. A cylindrical capacitor is a type of capacitor that consists of two concentric cylinders separated by a dielectric material. Let's explore the concept of capacitance for a cylindrical capacitor. The cylindrical capacitor comprises an inner cylinder with radius R1 and an outer cylinder with radius R2. The cylinders are aligned along a common axis, and the space between them is filled with a dielectric material. Surface charge is a key parameter in cylindrical capacitor. The surface charge is defined as the ratio of the charge on each cylinder to the area of cylinder surface. We express it as sigma equal to charge over area, where sigma represents the surface charge density, Q is the charge of each cylinder, and A is the area of the cylinder surface. The electric field between the cylinder plays a crucial role in determining the capacity of cylindrical capacitor. The electric field can be calculated using the formula E equal to sigma over E naught, where E represents the electric field, sigma is the surface charge density, and E naught is the permittivity of the dielectric material. The capacitance of cylindrical capacitor is given by the ratio of the charge on each cylinder to the potential difference between the cylinders. We express it as a C equal to Q over B, where C represents the capacitance, Q is the charge of each cylinder, and B is the potential difference between the cylinder. To derive the capacitance formula for a cylindrical capacitor, we integrate the electric field formula E equal to sigma over E naught over the distance between the cylinder. The integration leads us to the formula for the potential difference V equal to E times D, where D is the distance between the cylinder. The value of E from the electric field formula, we obtain V equal to sigma times E naught over D. Rearranging the capacitance formula, C equal to Q over B. We arrive at the final formula, C equal to 2 pi times E naught times length over load R2 per R1, where L is the length of cylinders. In conclusion, the capacitance of cylindrical capacitor is a fundamental property that depends on the radius, length, and dielectric properties. For a spherical capacitor, the charge enclosed by the Gaussian surface is constant and equal to Q. Thus, the electric field between the conductor is E equal to Q over 4 pi E naught R square. To find the potential difference, we integrate the electric field, as shown below, and integrate the above expression given. Finally, we can obtain the capacitance by dividing the charge Q by the potential difference V. C equal to 4 pi E naught times 1 over R1 minus 1 over R2. This is the expression for the capacitance of a spherical capacitor with inner radius R1 and outer radius R2 in a dielectric medium with permittivity E naught.
4.3.2 capacitor in parallel. We have battery attached to two capacitor parallel each other, and let's use a 10 volt. First capacitor 100 microfarads, second capacitor 200 microfarads. What is equivalent capacitance of this circuit for parallel circuit? Total capacitance is the sum of all the capacitor connected in parallel. So 300 microfarads. How much charge stored in C1? Q1 equals to C1 times V1. So you need to know the voltage across C1. In element circuit, the voltage across every element that's parallel to one another is the same, so they will all have the same voltage. Calculate Q1. So Q1 equals to 100 microfarads times 10 volt. So Q1 is 0.001 coulomb. Now what about C2? Q2 equals to C2 times V2 equals to 0.002 coulomb. Q total equals to Q1 plus Q2 equals to 0.00T. Now that, what if we have a capacitor circuit in series? Let's use 3 capacitors. So on the left we have battery. Let's call 50 volt and C1 is 2F, C2 is 3 farad and C3 is 5 farad. What is the equivalent of capacitance? So equivalence capacitance equals to 1 over C1 plus 1 over C2 plus 1 over C3 power of negative 1. So equals to 1 over 2 plus 1 over 3 plus 1 over 5 for power of negative 1. So the capacitance is 0.9677 farad. How can you find the voltage across each of capacitor? Sometimes you may need to find the voltage of just one of the capacitor. Next, we need to calculate the charge. Equivalent capacitance times voltage. The voltage across each capacitor will be different if the capacitance is different. In a series circuit, the charge stored on each capacitor is the same. In the parallel circuit, the voltage across each capacitor is the same. Make sure you understand the difference. So once we find Q, this Q will be the same as Q1, Q2, Q3. They all equal each other. Q equals to 0.97677 times 50 equals to 49.39. Let's find V1 is Q1 over C1 is equal to 48.39 over 2, so 24.2 volt for C1, and then V2 Q2 over C2 equals to 16.1 volt, and V3 Q3 over C3 equals to 9.7 volt. So the total voltage is V1 plus V2 plus V3 is equal to 50 volts.
Hi, I'm going to explain about subtopics 4.4 energy stored in charged capacitor. First, connect the non-charged capacitor with light bulb will result in nothing. And then connect the capacitor to the battery first to charge up the capacitor. And then when connect the charged capacitor with the light bulb lights up. This is because due to charging and discharging. First, charging. When a capacitor is connected to a battery, charges separate due to the battery establishing an electric field. Electrons flow from one plate to the other, creating a charge imbalance across the plates, which develops an electric field. Charging a capacitor requires external agent, which is battery, to do work to move charges. Initially, no work is needed as there's no electric field. As charge Q increases, so does the potential difference across the capacitor, necessitating work. The total work to charge from Q equal to 0 to Q is given by W equal to integral from 0 to Q over C dQ, which is equivalent to Q squared over 2C. The capacitor stored energy in the form of electrical potential energy. Work required to charge the capacitor is equal to change in potential energy. When starting from empty capacitor, the potential energy stored in capacitor is U equal to Q squared over 2C, equivalent to 1 over 2 Q times delta V, and also equivalent to 1 over 2 C times delta V squared. And then discharging. When a charged capacitor discharges, the opposite charges on its plates are thrown back together because opposite charges attract. The energy stored in the capacitor's electric field can be understood by its energy density, represented as this formula, which tells us how much energy is packed into each unit of volume within the capacitor's electric field, with permittivity being a constant and energy denoting the strength of the electric field.
Assalamualaikum warahmatullahi wabarakatuh. My name is Raya binti Hassan and my matrix number is S72518. I will continue with the last subtopic in this chapter, capacitor with dielectric. This subtopic contains into two parts, 4.5.1 dielectric constants, 4.5.2 capacitance of capacitor with a dielectric. What is dielectric? Dielectric are insulating material placed between the plates of a capacitor. They prevent direct electrical contact between the plates. Common dielectric material include paper, mica, ceramic, and plastic. As you can see in figure 1, there are two plates and there are brown balls called dielectric between the plates. Next, we continue with dielectric constant and it's denoted by epsilon. It is a property of material that describes its ability to store electrical energy in electric field. It also measures how effectively a material can hold electric flux within it. Different materials have different electric constants. The dielectric constant also affect other electrical property of material, such as their ability to conduct electricity. As you can see in figure 2, there are dielectric constants for different materials. For example, air is 1.0, lead is 4.9, mylar is 3.2, and nylon is 3.4. As you can see in figure 4, there is a setup on how capacitance of capacitor with dielectric experiments. The working principle of dielectric capacitor is relatively straightforward. When a voltage is applied, the electric field polarizes the dielectric material, causing a positive and negative charge to separate, leading the accumulation of charge on plate. The dielectric permittivity determines the amount of charge that can be stored for a given voltage. This ability to store charge makes capacitor vital in smoothing power supply fluctuation, filtering noise, and many other applications. To calculate the capacitance of capacitor containing a dielectric, you need to know the area of capacitor plates, the distance between the plates, and the permittivity of the dielectric material. The formula is C equals to epsilon times A over D, where C is the capacitance, epsilon is the permittivity of dielectric material, A is the area of the capacitor plates, and D the distance between the plates. The dielectric incapacitance significantly impacts capacitance. It increases capacitance by reducing electric field strength and allowing for more charge for storage. The dielectric constant determines the extent of capacitance increase. The presence of the dielectric increases the effective plate separation, thus raising capacitance. It improves voltage stability and enables capacitor to withstand higher voltage without breakdown. Dielectric material may exhibit temperature-dependent change in capacitance. Choosing the right dielectric enables customization of capacitance for specific application. Last but not least, I would like to add a daily life phenomenon involved capacitance in capacitor with dielectric. For example, I choose as electronic devices. Capacitors are widely used in electronics devices such as smartphone, computer, televisions, and radio. They are used for various purposes like energy storage, filtering, noise reduction, timing, and oscillation. For example, capacitor in power supply circuit helps to stabilize voltage level and filter for the unwanted electrical noise. So from electronic device, I choose 3 examples, which is energy storage, noise reduction, timing, and oscillation. First is energy storage. Capacitors are capable of storing electrical energy. In electronic devices, they may use as a short-term energy storage element. For instance, in a smartphone, capacitors are employed to store energy and provide quick bursts of power when the device requires high current, such as when you call someone. Capacitors act as a buffer, ensuring a stable and reliable power supply to the device. Second, noise reduction. Capacitors aid in reducing electrical noise in electronic devices, ensuring proper functionality. They act as decoupling capacitors, diverting high-frequency noise away from sensitive components through a low-impedance path. By absorbing and dissipating noise, capacitors help maintain signal integrity and minimize electromagnetic interference. Last but not least, timing and oscillation. Capacitors are utilized in timing circuits and oscillators. In electronic devices like television or radio, capacitors are employed to control the timing of specific operation of the frequency. of oscillating signals. By charging and discharging the capacitor at predetermined rates, precise timing interval or oscillation frequency can be achieved.